In the digital age, the amount of data we generate and consume is staggering. From texts and images to audio and video files, the demand for efficient ways to compress data has never been greater. In this video, we will embark on a journey through two fundamental techniques that revolutionize the way we store and transmit information. Let's assume computers employed fixed-length codes for compression, encoding each character with a uniform number of binary digits. While this might seem straightforward, a notable drawback emerges as both common and uncommon characters end up occupying the same space. An intriguing alternative inspired by the Morse code presents a more efficient solution where frequent characters are assigned shorter codes while less common ones adopt longer patterns. But there is a catch. To ensure unambiguous comprehension, Morse code necessitates costly periods of silence between each character transmission. A pioneering solution to this challenge was proposed by Fano, who introduced variable-length codes without the need for expensive spaces. By ensuring that no code shared the same pattern of digits as both as a complete code and the start of another, Fano could employ shorter codes for more common characters. To get a better understanding of this algorithm, let's try to encode the word locomotion using Fano's method. We start with a list of symbols and their corresponding frequency counts, reflecting their relative occurrences. Next, we sort the symbols based on their frequencies, with the most common symbols on the left and the least common ones on the right. Then, we divide the list into two parts in a way that the total frequency count on the left is approximately equal to the total frequency count on the right. The path on the left branch is assigned the binary digit 0, while the path on the right branch is assigned the binary digit 1. This means that codes for symbols on the left branch will start with 0 and codes for symbols on the right branch will start with 1. The process is then repeated recursively for each of the two halves, subdividing groups and adding bits to codes until each symbol becomes a corresponding code leaf on the tree. The code for each letter is defined by the path from the top of the tree to the bottom. The result is a variable-length binary code where more frequent symbols have shorter codes, enabling more efficient data representation and compression. The outcomes were astounding, achieving efficient compression that significantly reduced data size. But it's essential to acknowledge that Fano's method was an approximation since he constructed the trees from the top down, aiming to maintain a symmetry between the paired branches. In the year 1951, Robert Fano gave the students in his information theory class a unique opportunity: either take a final exam or tackle the challenge of enhancing a leading data compression algorithm. This is where David Huffman, a brilliant information theory student, stepped onto the stage, forever altering the way we compress and transmit data just to avoid his final exams. In Huffman's method, we start by grouping two of the less common characters, let's say I and N, together as if they were a single letter. Next, we update the frequency chart, giving us four choices: the letter O, which appears 4 times, the newly combined IN node, which effectively appears twice, and the individual letters L, C, M, and T. From these two options, we again pick the two least common characters, M and T. The chart updates again. 0 still has the frequency of 4. IN and MT now each have a frequency of 2, and the letters L and C remain on their own. We continue the process repeatedly, grouping the two least frequent options, updating both the tree and the frequency chart. The resultant tree can be used to obtain the code for each character, just like we did in the case of Fano's technique. While it may seem like a small difference, Huffman's method can save a single bit in the encoding process. For shorter text, the difference may seem negligible, but as you scale up to compressing extensive documents, databases, and multimedia files, the savings becomes exponential. In fact, these methods have left an indelible mark on the digital age, making data transmission and storage more efficient than ever before. What's even more intriguing is that these early pioneers inadvertently laid the foundation for countless compression algorithms that we use today. So, the next time you zip a file or stream a video, remember that it all started with a quest to avoid a final exam. In the grand tapestry of technology, every bit and byte owes a debt to these curious minds.